All right, welcome everybody. Welcome to the Rutgers Geology Museum late night. Our May late night and last for this academic year will be on the topic of meteorites, and we are very happy to have a great night planned for you with our traditional trivia by now, a craft, and then we will follow with Dr. Juliane Gross presentation directly from Texas. So, are we ready, Lauren? We are going
Sorry,
to.
I had to unmute myself. Yes, we are ready.
All right. So, Lauren and I will be guiding you through our trivia late night today. We have. Let me move my slide. Okay, so we have here the QR code for you guys, so you can scan your devices, and that will take you to the www.menti.com. And that when you're there, you're going to enter your 8-digit code 40522211. And then we can see your live answers for the trivia questions. You should keep track on your own also for the purposes of knowing how you did. So we will see at the end how good of a meteorologist you are or geologist. So we're going to go ahead and start with question number 1. So get ready, get your paper, your pencil, and the first question is, when a meteoroid, a space rock, enters Earth's atmosphere, it becomes A, meteor, B, asteroid, C, meteorite, or D, comet.
Okay, so we have most answers for C right now, some for B. Good. Oh, here comes one for A. There's a spread. No one's picking D, comet.
All right. So let's go.
Most are saying C at this point.
Meteorite. Okay, let's see. And the correct answer is meteor. When meteoroids enter the Earth's atmosphere, they burn up as they travel through it and become meteors, which are also known as shooting stars, right? So if you have ever made a wish to a shooting star, you're actually looking at a meteor, okay? Let's go on question number 2. If a meteor does not vaporize during its trip through the Earth's atmosphere and lands on the planet's surface, it is called A, comet, B, asteroid, C, meteorite, or D, tectite.
All right, we've got answers for all 4 right now.
Okay.
Give them another couple seconds. Oh, right now it's sort of tied between B and C.
All right.
And now A is pretty close too. Very evenly spread between A, B, and C.
All right. So let's go ahead and take a look at the right answer. And the right answer is meteorite. Meteorites ranges in size from microscopic, very tiny particles to the size of a football field. However, larger meteorites usually break up upon the impact on Earth, so you can find multiple pieces in one area from the same meteorite. All right, so let's go on. Question number 3. Where do most meteorites come from? A, the moon, B, Mars, C, the asteroid belt, or D, beyond our solar system? Where do you think they come from?
All right, we have people picking C and D right now. One just came in from Mars. It's overwhelmingly picked answer C, the asteroid belt at this point.
All right. Okay, so let's check it out. And you guys are experts. That is the correct answer. All meteorites come from within our solar system, right? If not, it will be too far away. but most are asteroid fragments that come to Earth from the asteroid belt between Mars and Jupiter. And you can see that right here is the purple circle. I believe that each dot represents an asteroid floating around, and sometimes they can come up and crash on land or planet Earth right here. All right. Question number 4. How old can a meteorite be? 1 million years old, 500 million years old, 1 billion years old, or 4.5 billion years old? This is a tricky question.
So right now we have every answer being picked. It's very close numbers between A, B, and C, but most people are picking D.
Okay, let's see. Correct again, guys. Great job. Most meteorites come from asteroids, which are bits of planets that never, I practice this word, collapsed when the other planets in our solar systems were forming. So this means that many meteorites formed before Earth became a planet, right? And you can see a nice picture here. All right. Question number 5. There are 3 main types of meteorites. Which of these is not a type of meteorite? The icy meteorites, the stony meteorites, the iron meteorites, or the stony iron meteorites? Which one you think does not exist or is not a type of meteorite?
So we have about equal numbers picking A and B. But most people are picking D right now, stony iron meteorites. That's the overwhelming response.
All right. Actually, the answer is icy meteorites. If we look at the families of meteorites, they're divided into 3 types, right? They're based on their composition. So we can have stony meteorites right here, made out of rocky material, or the iron meteorites that look more metallic. They're made of metals. And then we can have a mixture of that. Stony iron meteorites are a mixture of the rocky material with the metal. So which was your favorite? Let us know in the chat.
This is something Dr. Gross will talk about more when she does her presentation later tonight.
Exactly. Great. All right. So let's see. Question. Oh, before we go to question number 6, if you just joined us and you were late in the beginning, you can scan the QR code here and go to www.menti.com and enter an 8-digit code for playing with us so we can see your live answers. And the code for that is 40522211. And keep track of your score, okay? So we will continue. We will move on to question number 6. Question number 6 says, comets are different from meteoroids because they are made of A, rock, B, ice and dust, C, metal, or D, liquid.
Okay, still waiting for some answers to come in. We've got people picking A through C right now. But the runaway answer is B, ice and dust.
All right, let's see. And guys, you were correct. Comets are made of frozen gases and dust. And if you see a comet in the skyline, right, it passes by the sun, it will heat up, forming a glow tail of dust and gases in the background. So you will see it in a different way. You will see that line right behind it. All right. Question number 7. What is the name of the largest meteorite ever found on Earth? Hova meteorite, Cape York meteorite, Willamette meteorite, or the Agenda meteorite? Which one you think is the largest?
This one is pretty evenly split between all answers.
Come on, someone
I did not
vote.
know the answer to this one either. But pulling ahead is A,
Okay,
meteorite.
excellent. So let's see. You were right, guys. Yes, you can celebrate like the person on top of the meteorite. The Hobart meteorite is the largest known meteorite in the world and is located in Namibia in Africa. It measures 9 feet by 9 feet and is 3 feet tall and is estimated to weigh about 60 tons. So nobody is moving it anytime soon, correct?
It's stuck
Okay.
there.
Question number 8. What is the name of the largest meteorite ever found in the United States? Right? So A, Peekskill meteorite. B, the Agenda meteorite. C, Sighot Allen meteorite. Or D, the Willamette meteorite.
All right, again, a very evenly split answers. We are tied for answers B, C, and D at the moment.
Okay. Let's see. And it's D, letter D. The Willamette meteorite was found in Oregon and weighs about 17 tons. Pretty big, huh? And because it was not found within an impact crater, scientists believe it crashed somewhere in Montana or Canada and was transported to Oregon by a glacier. And you can see here the picture, right? It looks pretty eroded to me, so the story makes sense in my head. So I hope it makes sense in your head too. All right, so let's go to question number 9. Question number 9. How many people have been killed by falling meteorites?
All right, most people are saying there's a lot of people killed, 31. And there's a pretty even split between 1, 4, and 22.
All right.
Actually, now we're pretty close between B and C
Okay.
and D.
I have to say I was surprised by this.
Yeah, me too.
Okay, so let's check it out. It's actually A. On record, it's only one person have been apparently killed by a falling meteorite. And it is believed that this single person was killed in August of 1888 in Iraq. And there's an ancient record of the event that was recently discovered in Turkey. But certainly there's no record. So it's the best accident ever because you have very low probabilities to die, although many people have been hurt before, right? So let's move on to question number 10. How much space debris and space dust falls to Earth on yearly basis? Every year, how much space debris and space dust falls into Earth? A, 2 tons. B, 1,000 tons. C, 2,700 tons. Or D, 5,200 tons.
All right, another good split between the answers.
Mhm.
In the lead is A and B, but have not far behind C and D.
And I have to say, I never thought about this, right? I never thought about
That
how
dust can
much
add
will
up to this
come
much. Yeah.
in a year. So let's see. Let's check out that answer. And it's actually D. Is 5,200 tons. So, but in contrast, it's estimated that only about 10 tons of larger visible meteorites fall into Earth each year, right? So, we have constant dust, but then we have a little bit of more visible pieces that Dr. Gross will be telling you about her expeditions and her trips to find these guys, right? All right, so let's go and announce again our QR code. So if you join us late or if you lost your in your desktop where you were, just go again to www.mentee.com and you will enter your 8-digit code, and that is 40522211. And we can that way we can see your live answers, and you should also be keeping track of your answers on a piece of paper. Okay, so let's move on and go to question 11. When the Earth encounters many meteors at once, we call it a meteor shower. How do scientists name these meteor showers? A, after the constellation from which they appear to be falling, after Roman gods and goddesses, after the person who discovered it, or the after the month in which it occurs.
All right, so we have a few people picking B and C, but the overwhelming response is A at the moment.
Okay, and you guys surprised me. Yes, that is the correct answer. Meteorite showers are named after the constellation from which they appear to be falling from, and we have an example here. If you look at the picture, the Orionids meteor shower that is visible each October appears to be coming from the Orion Hunter constellation. Question number 12. About how many meteor showers occur per year that are visible to observers on Earth? A, 15, B, 30, C, 50, or D, 100?
All right, so we have answers A through C. Right now, no one's picked answer D. But A at 50, oh, there goes one person picking D.
Yes, thank you.
But most of them are picking A, 15. Oh, B's coming close. So it's pretty close between A and B right now.
All right, so let's check it out. It's actually B. Good job. B, 30. So some meteor showers have been around for hundreds of years, and the Perseid meteor shower each August was first observed 2,000 years ago in China. So we have these curious facts, and we hope that you sometime have the opportunity to experience seeing live one of these meteor showers. We're going to move on to question number 13. And it says, which of these is the largest and most visible meteor showers? A, Orionid meteor shower. B, Perseid meteor shower. C, Leonid meteor shower. Or D, the Geminid meteor shower.
All right, we're pretty tied between A, B, and D right now.
Okay.
One person picked C.
Let's see.
Yeah, it's pretty close between all four of them right now.
It's the Perseid meteor shower. This meteor shower is the largest annual meteor shower and peaks on August 12th of each year, with one or more meteors visible per minute. So it will be a pretty cool activity to do in August. All right, so let's move on. Question number 14. How fast can a meteor travel when it first enters Earth's atmosphere? A, 8,000 miles per hour. B, 50 miles per hour. C, 160,000 miles per hour. Or D, 200,000 miles per hour.
All right, we've got people picking all four answers.
Okay.
but most of them are going for C, 160,000 miles per hour.
Okay, let's see. You were correct. Great, guys. Very exciting. So meteors can be traveling up to 160,000 miles per hour when they first enter the Earth's atmosphere. Atmospheric drugs causes them to slow to between 200 and 400 miles per hour when they hit the Earth. So they may come at that speed, but it's going to be slowing down as it comes down. All right. Question number 15. What is the name of the car-sized meteorite that exploded over Mexico in 1969? This should be easy. A, Agenda meteorite. B, the Juliane meteorite. C, the Hodges meteorite. Or D, Canyon Diablo meteorite.
So we have all options being selected.
Mm-hmm.
But the second runner-up right now is A, Allen D meteorite, and then the number one is D, Canyon Diablo meteorite.
Okay. I have to tell you guys that I doubted between A and D too, but Canyon is written in English. So I went with A, Agende. This is a common Hispanic last name, and that was correct. So the Agende meteorite was traveling at about 10 miles per second before it exploded over Mexico on February 8th of 1969. So imagine the impression of walking around and seeing that happen. Question number 16. What is the name of the meteor that exploded during its descent over Russia in 2013 and injured 1,200 people? A, Agenda. B, Shelbyasky. C, Moscow. Or D, Pixgill. And you know to eliminate at least one of them by now, right? So let's see.
So yes, we've got people selecting all of them, but it is overwhelmingly answer B, and I'm very impressed of you attempting to pronounce that because I
I
cannot.
practiced the whole afternoon, so so these you're correct, guys. It's the Chelyabinsk meteorite, and actually I love the fact that this one we have the actual picture of it coming down because it's all over the internet. People were able to record it. So to me, that's the importance of technology, right? Like we get to be witness of these things happening because of access to technology. So this 66-foot diameter Chelyabinsk meteor entered Earth's atmosphere on February 15, 2013, and over 1,000 people were injured as a result of its explosion, but luckily no one was killed. So we're not adding to the list. We only have, over the recorded history, only one person have ever died because of an incident like this. Question number 17. How many impact craters have been discovered on Earth? A, 15, B, 85, C, 190, or D, 410?
All right, we've got all four answers being selected. B and D are closely tied for second place, but first place right now is C, 190.
All right. And C is the correct answer. So impact craters are relatively rare. Only about 190 craters have been confirmed to be caused by an extraterrestrial impact. And you can see in the map those locations and how I was surprised at the variety of sizes, right, of the impact. So let's move on question 18. Of the known impact craters, how many of them are located in the United States? A, 5, B, 15, C, 25, or D, 30?
This might be the most even split between all four of them right now. Although A is pulling ahead. Oh, no, I spoke too soon. Now A and B are the two most popular answers.
All right. And actually it's D, 30. 30 of the 190 known impact craters are located in the United States of America. They are widely distributed around the country, with the nearest one located in Virginia, Kentucky, and Tennessee. And so that means road trip this summer, right? Let's go and see some of these. Question number 19. The best preserved impact crater in the United States is located in which state? A, Arizona, B, California, C, Utah, or D, Wyoming?
We have people picking every answer. B, C, and D are pretty evenly split, but A is the overwhelming majority.
Okay. And actually, guys, you are correct. It's A, in Arizona. This meteor crater, also known as the Behringer crater, is an impact crater located outside of Flagstaff, Arizona, and it has a diameter of 0.8 miles, almost around a mile, and is open for tours. And I believe some images of this were used in one of the Avengers movie or the Thor's movie. So that's how I knew it was in Arizona, because I remember reading about it before. So question number 20. The impact that scientists believe killed the dinosaurs occurred in which modern day country? A, Bolivia, B, China, C, Mexico, or D, Russia?
All right, we have a handful of people picking D, but overwhelming response says letter C, Mexico.
All right. And that is correct, guys. That's at the peninsula of Yucatan, Mexico. The impact crater is buried underneath the Yucatan Peninsula of Mexico and is estimated to measure about 93 miles in diameter. So you can see this is huge over here. And now it's time for you to tally your results, and you're going to tell us how many questions did you get correct? Are you a space enthusiast with 8 to 10 questions correct? Or if you had anywhere between 11 and 15 questions, we will consider you an astronomer tonight. Or if you had between 16 and 20, you are a meteorite specialist. You're an expert, right? So thank you for playing with us. This is always really fun. We hope you learned something new tonight and that you validated your knowledge. So let us know in the chat which is your classification. And now Lauren and I will go away because Ria is actually planning a very fun activity next. So I'm going to go and put here the slide for her. And when she's ready, she's going to come into the presentation, and she's going to talk about awesome asteroids. So if you have clay or Play-Doh and a spoon, and if you have sand or pebbles, you can go grab those when Ria gets here, and we will continue with you shortly. Also, you can QR code these, you can scan this QR code so you can go into the Padlet.com at the Geology Museum for Meteorites. That way you can take a picture of what you build and show us what you're working on.
Thank you, Patty. So hey everyone, my name is Ria, And as Patty mentioned on the slide, you can see we are going to be making our own asteroids. So, but I'm going to talk a little bit about asteroids before that, but just get your items now. You can grab some clay or Play-Doh. You can get a spoon if you want, and some sand, pebbles, or if you don't have pebbles, you can get some small objects to represent the minerals and different rocks and grains in your asteroids. So if Patty, you could show me the next slide, then I can start talking to you guys about the asteroids a little bit. All right, so asteroids are super cool, and you guys did such a great job in the trivia, and you guys got a lot of these answers right. So asteroids are really old, right? So our Earth is about 4.56 billion years old, and asteroids, like you guys answered in the trivia question, asteroids are also about 4.5 billion years old. So they're as old as our solar system. And so how our solar system actually formed is there was a big cloud that was full of gas and dust and debris. And so it starts spinning. And as it starts spinning, it starts to flatten out, kind of like when you guys have ever seen like pizza dough when they like are spinning the pizza and it gets really flat and cool. So you can think of that. You can think of this cloud that became like kind of like this disc, rotating disc of gas and dust. And so a lot of the particles and the dust and particles start condensing in the middle, and that formed our sun, right? And so then the other pieces, so as it's this flat disk, you can kind of see that in the picture where the sun is in the middle, and other pieces and other bits are condensing around that to form our planets. And so all of the leftover rocky material that, excuse me, didn't get to be incorporated into the planets actually became the asteroids. And on the next slide, we will see that. Yeah, so here are some pictures of cute little asteroids, right? That's not what they actually look like, but there's a little diagram. So asteroids can be pretty similar to planets. Some can be small, some can be even be larger. So they have a really large range of sizes. Most of them, like you guys saw in the trivia questions, most of the asteroids are located in the asteroid belt, which totally sounds like a rock band, but it's located between Mars and Jupiter, and that's where most of them come from. And other ones can be found on like orbital paths of some planets, even Earth. Next slide. All right, so I'm not going to talk too much about asteroids because Yuli has an awesome presentation for you guys, but I just want to mention, like, so here's kind of the structure of like there are different types of asteroids. So here's one kind in the picture here. So you can see it has a core, there's a mantle and a crust. Some asteroids are even partially melted. Some of them are just completely melted. And so those asteroids that have the completely melted also have the core, which is made out of iron and nickel. And the Earth also has a core made out of iron and nickel, although the Earth's core is solid and it's not molten. But there are many different kinds of asteroids, which I'm not going to get into the details because Yuli has a really great presentation to show you guys. Next slide. Okay, so here you can see like the different sizes and there are different shapes. So because asteroids formed all over the solar system, some of them might be more like angular. They kind of have like jagged edges. Some might be really nice and rounded. Some are like just really bumpy. So they come in all shapes and sizes. Some of them contain metals, right? We'll learn more about what they're made out of. And some of them are made out of rocks and some contain clay and different types of minerals. And so these asteroids, like I said, can be boulder sized to hundreds of miles in diameter. So the asteroid that killed the dinosaurs was about 6 kilometers and I think 6 miles. I forgot, but it was pretty big. Next slide.
10 miles and 6 kilometers, I think it's about.
There, yeah, there we go. I was right. It was 6 kilometers and that's 10 miles. All right, so now I'm gonna switch my camera view so you can see how to make an asteroid. So you can grab clay, Play-Doh, you can get a spoon, sand, and pebbles. So I am going to switch my view here. All right, so I have a couple of different things here. I have some modeling clay, which I'm gonna take out. I also have Play-Doh, so I'll make a couple of different kinds. And you can get any color you want. These are just the ones that I have. So mine is going to be a very bright orange. All right, so I'm just making like I'm gonna make it kind of like a circle. And I have these Lego pieces. So I'm going to use these Lego pieces to represent like different pebbles and rocks in here. I'm just gonna stick them on. All right, so here's one of my meteorites. And I have a box of sand. I have these two rocks in here. But what I'm gonna do now is I'm gonna make another one. And this one maybe I'll make a little less like a circle. But now I can actually dip this in some sand. I'm putting some sand on here. I'm gonna roll it around a little bit. Now I have some more pieces of Legos to stick on here. Maybe I'll put some more sand on that. So I'm gonna stick this on. And you guys can make your meteorites, and you can then take a picture and post them to the Padlet so we can see your awesome meteorites and see what they look like. So you can share those pictures with us. All right, so I have two different kinds here. And I also earlier made some edible meteorites. So I'm gonna put my clay ones on the side. So I made a meteorite like this. So I took a Rice Krispie and I had M&Ms and I crushed up an Oreo. And I actually even put a little bit Nutella inside, and I molded it into this ball shape, and I put these M&Ms in here, and then I rolled it around in the crushed Oreo. So here is my edible meteorite. And now if I go back to this one, so to my other clay ones, I could also make some craters in here. So I'm gonna use this circle thing I have, make some craters. So I just made a really huge crater here. I don't know if you guys can see that. It's a big circle there. And I can make another crater. Here's another really big, giant crater. So you can make craters with your fingers, or you can make it with a spoon, or anything that you have. You can make some craters on yours. All right. Because these meteorites, they hit each other, they break apart. There's a whole bunch of things that happen. And so yeah, just take pictures of your creations and share them to the Padlet. I'm gonna check if you guys have any pictures on here. Let's see. All right, I don't see any pictures yet, but oh, let's see. So I'll share the Padlet with you guys. This is what it looks like. And here you can take a picture and you can post it up here. So here are some examples. So these are some really nice ones here. Here are some instructions if you guys want the detailed instructions of how to make your own asteroids. There's this whole document here with the materials and even different pictures of actual meteorites. And here's the QR code if you guys want to scan that and upload your creations here. Lauren or Patty, did you guys make any?
I did not. I do not know where any of our Play-Doh is. We've had some accidents with it from homeschool. So it's been banned in our house.
Oh, look at Patty. Patty made a really nice one. Is that an edible one?
It's not edible. It's a rock and it's painted. And it also has a screw in the middle because it's a hole. So I fill it up with metal. So I have
It's a pretty one.
An iron stone.
Yeah,
Ironstone meteorite in here, right here.
that's a pretty one.
I see some pictures coming in being posted to Padlet, so there might be some to share.
Oh yeah, oh I see a bunch. Yeah, let me share that with you guys. Oh, this is really nice. Look at this. Nice job. I like these. Oh, that's a
Like the
really good
oblong
one.
shapes of them. Oh, that's cool. I
Yeah,
like that one.
that's a really cool one. Yeah, and this one is really cool too. I like that one. Yeah, so keep sending in your keep posting pictures of your asteroids, and we you can even post them on social media and you can tag the Geology Museum. We would love to see that.
We are on Twitter and Instagram at RUGOGEO Museum. So please tag us. We'll
Oh,
reshare pictures too if you tag us on them.
I think I see a drawing here. Oh, that's
Oh,
I
so
like
nice.
that.
Yeah, I
Yeah,
love
so
that.
I like the diagram of the Rice Krispie and edible asteroid with M&Ms and the other one. Nice job. Yeah, so keep posting your creations, guys. All right, so I think are we ready to move on to the next segment of our night?
I think so.
Yeah.
Dr. Gross, are you around and ready?
Yep, I'm here.
All right. Rhea, if you can stop sharing your screen.
I think I did.
I still see it. Maybe that's just me.
I see it too. Okay,
There we go.
now.
There. It's just slow. So go ahead.
Should I
Julie.
share? Okay.
Yep, go ahead.
Hold on. Oh. Present. Okay, can you see to the laser pointer and okay, you can all see the screen?
Yes, we can see the captions and we can see your laser pointer. So great.
Great.
So I'll give a very, very brief intro. We are very thrilled to have Dr. Juliane Gross give a presentation on meteorites. If you have been to museum events of ours before, Dr. Gross is a frequent presenter for us at different events. We'll actually post it in the comments section, but she has given a whole talk for the museum before. Actually, I don't know if we have it videotaped, but she has given a whole talk before about how she collected meteorites, which she will mention some of this. She's a professor at Rutgers University, but right now, which is the really cool part of her job, she's at NASA and she's working on Apollo samples. So she's got the lucky privilege of being one of the few scientists who gets to open and do the initial scientific analysis of the Apollo samples that were collected over 50 years ago. So some really, really cool stuff that she's doing right now. So anyway, without further ado, Dr. Gross, please tell us more about meteorites.
All right, thank you, Lauren. I'm very excited to be here and talk to you guys about one of my most favorite topics, and that is meteorites. And I'll show you a few pictures from Antarctica where I went 2017-18 in the field season, and you can see one of the meteorites here on the blue ice sitting right there, and here's me all bundled up so I'm not cold with a little meteorite right in front. So I'll talk about that in a little bit. All right, so if we look at our solar system, and this is an artistic view of our solar system, where we have the inner planets, right? There's Earth right here and our moon, and then the asteroid belt, which you have already heard a lot about today, and then the outer planets, the gas giants. When we look at this picture, there's a lot of questions that people like me as scientists ask, but also I'm sure that you all have asked yourself a lot, like, you know, where do planets come from and how do they form? And what are the building blocks of planets? And what did Earth look like before there were humans and dinosaurs? And how old is the Earth? And how old are the other planets? And how old is our solar system? Like, how do we find out answers to all these questions. Where does life come from, right? Where's the water coming from on Earth? And so you would think, because we are living on a planet, if we zoom into Earth here, right, that we can, as geologists, just go around and we can pick up some rocks and we can answer all these questions. But the problem is, if you look at our planet, and it's a very, very beautiful planet, but most of the surface is covered in oceans, right? And our planet is geologically very active. And so we have weathering going on, and rain and wind, and all these elements, they break rocks apart and they turn them into something new. So they make sediments, and then we have plate tectonic that subducts material into the interior where it melts, and then all the rocks get reset. So all this old geologic evidence has been destroyed and recycled and turned into something new. So if we want to learn something about the very early history of our solar system and the very early history of Earth and other planets, then we need to find material that hasn't changed since their formation. So I'm going to take you on a little tour of how the solar system formed and how the first rocks in our solar system formed and where we can find them today. So if we turn the clock back, a long time back, about 4.5 to 4.6 billion years ago, this is what we think our solar system looked like. So in the center is a protostar. So it's not quite a star yet, but it's a protostar. And then we have this swirling disk of dust and gas. And if we had a microscope, and we could look right in here into that gas disk, and this is what we would see. They're little itsy bitsy tiny mineral grains that crystallize directly from that gas cloud. Now these tiny particles, they start to stick together through electrostatic forces. And that is best explained. You all know what that is, electrostatic forces. So if you have a balloon and you rub it on your head, your hair will stick up because of electrostatic forces. Or if you have a unfortunate furry friend who gets into places where they shouldn't get into, then all the little styrofoam balls might stick onto their fur because of electrostatic forces, right? And some of you might have also done some vacuum cleaning at home. So if you have hardwood floors and you've removed them, oftentimes what we see are dust bunnies, right? There's a lot of dust, and the dust clumps together and forms dust bunnies, and that is through electrostatic forces. And so these little tiny mineral grains that come from the gas cloud, they stick together just like dust bunnies. And so we can actually call them glorified space dust bunnies. And so now you have these space dust bunnies floating around, and then through a process that we as scientists, we haven't understand this yet. This is an active part of research. These little particles, they melt. And so now you have little molten droplets of lava floating around in space, and they're round because there's no gravity in space, right? And so they're nice and round. And then these little droplets, they crystallize into an object that we call chondrules. And so they're just round, and then they crystallize and become solids. And then these chondrules, together with some of the mineral grains and the dust, they all clump together and they form the first solid rock in the solar system. And these rocks are called chondrites because they're made out of these little chondrules. And so here's a chondrite, a meteorite, and you can see the round shape, all these little round parts that are in there. These are little chondrules. Sometimes they're elongated like this one because it got smushed when it was still warm. But this is the very first solid in our solar system that formed. And we can age date these rocks, and it turns out they are 4.568 billion years old. And because that's the first rock that ever formed in the solar system, therefore we can say the solar system is at least 4.568 billion years old. Now we have lots of these little rocks floating around, and then what happens is that these are the building blocks of planets. So these little rocks, these chondrites, were around first, and they started to clump together. And then they form objects that we call asteroids. And then they become bigger and bigger and bigger. And eventually they start getting really warm on the inside because you squeeze everything in really hard. And the bigger you become, the hotter it becomes, right? And eventually the inside starts to melt. And now this is where gravity comes in. So once you start melting, all the heavy particles, all the heavy elements, they start to sink towards the center. And so all the nickel and the iron and some sulfur, they all start to concentrate right here in the center. And all the light stuff, that starts floating onto the surface. And so in the end, you make a planet where we have a core where all the heavy stuff is located. Then we have a mantle where the intermediate stuff is located. And then we have a crust where all the light stuff is located. And so that's how you form a planet. But very, very early on in the solar system, there were lots and lots of planets and lots of baby planets and lots of asteroids. And if you have something that is very crowded, there is always going to be collisions or bumping into. So if you imagine there's a big crowd, everybody's on a big market, and you try to go through the market through all these people, you will bump into other people. Or if you're on a busy street and there are lots of cars and people don't use their blinkers, right, and they just swirl, then there will be collisions, there will be accidents. And the same thing happened in the very early solar system. So here is a planet, right? And here's a cross section. So if we would cut that planet, this is what we would see. Here's the inner core and the outer core. There's the mantle in green, and then in gray, there's the crust. Now, when we have a lot of collisions, we can get pieces that get blasted off the surface, right? So you can see here where things get blasted off. If we have bigger collisions, then we can even expose parts of the mantle, maybe some parts of the core or the outer core. And then if we have catastrophic collisions where the entire planetary bodies, they get ripped apart, we can also expose the core mantle boundary, and we can even expose the center, the core of a planetary body. And so this is where the meteorites come from. And now based on this, we can categorize them into 3 different types. And so the very first one, and that was one of your trivia questions, right, are stony meteorites. Now, if we look at our world collection, 79% of all our meteorites are stony meteorites. Most of them are chondrites, right, which are the ones that are pre-planetary, so they're coming from asteroids. And you can see here the picture I showed you before of the chondrite with the little chondrules in it. And then the other stony meteorite, they come from planets. And so these we call achondrites. So we just put the letter A in front of chondrites, and that just means not a chondrite. And so you could also call them planetary meteorites, for example. So here's a picture from Mars. This is one of the Martian meteorites that I work with, and you can see the black fusion crust, and I'll talk about that in a little bit. This is what the inside of the rock looks like. And so we think that particular meteorite comes somewhere of the mantle of Mars. And so if there are big impacts that happen on these planetary bodies like Mars, we can get rocks from the mantle or the crust. Now, the second type of meteorite are stony iron meteorites. And these represent the core mantle boundary. And they're the most precious meteorites we have. We only have 0.6% in our world collection are actually stony iron meteorites. And so this is what it looks like if you would find it. The metal gets kind of rusty a little bit, but if you cut it and you polish it, all the metal here is white. And then the minerals from the mantle are green. These are olivines. And so they are part of the mantle. And then the white is the metal, which is part of the core. And then the third category is if we have these catastrophic collisions of planets and we start exposing pieces of the core, and then they make iron meteorites. And so here's what an iron meteorite looks like. And if you cut it and polish it, you can see it's like nice and shiny. And then if you put acid on it, you can actually reveal the crystal structure of the metal. And this is what we call Wittmann-Stetsches pattern. And on Earth, we do not have the technology to actually make this pattern. So when metal cools very, very slowly, and I'm talking about thousands of years. So if you have a little metal droplet and you cool it so slowly that it takes thousands of years to cool, then metal actually grows in a crystal structure. And so this is what you see here. And so if you have an iron meteorite, or maybe you have a piece of iron and you don't know if it's a meteorite or not, if you etch that piece of metal and this pattern appears, then you know for sure that that is a meteorite, because there's no other way to make this. All right, so these meteorites are really, really important because they basically represent windows into the interior of planets. So we don't have the technology to drill into Earth and look at the core of Earth. We don't know what the core of Earth looks like, right? So the only way for us to understand and maybe make some experiments is by looking at iron meteorites that we know represent the core of other planetary bodies. Same thing happens for mantle material and even crust. And so once we learn how planetary bodies differentiate, basically how they make their layers, then we can apply that to Earth and understand our own planet better. And so once these meteorites, or these meteoroids, I should say, are blasted off into space, if they're small, we call them meteoroids. If they're really big, they become asteroids. Now they float around in space, and eventually, if they're lucky, they get captured by Earth gravity, right? So if this was Earth here, as meteoroids, and then they enter the Earth atmosphere, right? And so because of the friction, the outer part of the meteorite starts to melt, and it gets really, 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 really hot. And that's what we call the shooting stars that you can see at night, or the scientific term is meteors, right? And then if they don't burn up in the atmosphere, if they actually make it all the way to the ground and they touch the ground, that is then what we call a meteorite. And you can see how dark it is on the outside. So all the meteorites have this crust that happens when they go through the atmosphere. And this is what we call a fusion crust. It's only like a millimeter thick. It's very, very thin. So when the meteorite enters the atmosphere, this part that melts and makes that crust, it gets ablated all the time. So it stays really, really thin. And so only the outside gets very hot. The inside of the rock is extremely cold because outer space is very, very, very cold, and rocks are not good conductors. So if you ever read an article where somebody says, oh, I found a meteorite, and when I picked it up, it was extremely hot. Clearly it has to be a meteorite, and I saw it falling. Well, chances are that there was a rock sitting in the sun and somebody threw it at you, and that's what you saw, okay? So be careful with weird, sensational comments about where meteorites come from. Anyways, let's get into where we actually can find meteorites on Earth. So if you look at our beautiful planet, right? Where do you guys think meteorites land? And I don't know if I can see the chat. I do see the chat. So if you want to put in the chat, I'm going to give you a couple seconds. Tell me where you think on Earth meteorites fall. What do you guys think? Mexico. Yes, yep, absolutely. That's right. That was one of the trivia questions. There definitely was one in Mexico. Ria's mom says the ocean. Yeah, absolutely. Everywhere. Yes, absolutely. So that's right. Meteorites actually in the future, can Earth get a ring? We'll talk about that in a little bit. So in the USA and Antarctica, yes. So the big takeaway message here is that meteorites fall all over the Earth, everywhere, every day. Now the problem is, and you can see this in this picture, right? 73% of the oceans are covered. 73% of the Earth is covered in oceans. So that means 73% of the meteorites actually land in the oceans, and then we can't get to them, and then they're lost for science forever. Now, let's say a meteorite falls in the US, but nobody sees it falling, then it's going to sit there, right? Let's say in a field or in a forest, and nobody knows it's there. And then we have wind and rain and sunshine, and maybe a cow steps on it or a car drives over it, right? Plants grow on it. So that meteorite is just going to weather away and turn into soil. So our best bet to find meteorites are actually deserts. And let me see, why can I not advance this? There we go, deserts. So we have two types of deserts on Earth. We have hot deserts like the Sahara or Northwest Africa. So this is the picture with the meteor that I showed you here. This is from a hot desert taken. And then we have cold deserts on Earth, and the coldest desert on Earth is Antarctica. So this is Earth but rotated to the South Pole. So this is what Antarctica looks like. Now the deserts are great because there's so little participation and so little fauna and flora going on that the meteorites actually get preserved in their original state in there. And so Antarctica, if we zoom in here, if a meteorite falls in Antarctica, that's great because it's a continent. And so you can see here, this is what Antarctica looks like without the ice. And here's, you know, the ice shield basically. And so Antarctica is covered by about 2 miles of ice. And interestingly, it is still the driest place on Earth, even though it is covered with all this ice. Now, if a meteorite falls in Antarctica, it gets frozen into the blue ice shield somewhere on top, right? And that protects it from weathering away. It protects it from the wind. It protects it from liquid water, from weathering. Now the ice plateau, the ice shield moves. So it goes from the high point, the plateau of Antarctica, and it slowly flows towards the coast. But if the ice shield encounters obstacles like a mountain, and because Antarctica is a continent, there are mountains on Antarctica. So if the ice flows against a mountain, it kind of stalls. It can't go much further. And because the wind is so dry in Antarctica, it starts to ablate the ice. And so all the meteorites that are frozen in at different times and at different depths in the ice field now, they slowly get pushed to the surface and then they just sit there. And so all you really have to do is you have to go to Antarctica and then rescue all the meteorites that you can find. And so every year NASA sends 8 people into the deep field of Antarctica to go and recover these meteorites. And so I was lucky that I got to be one of those 8 people in 2017 and 18 to actually fly to Antarctica onto the ice plateau and start recovering meteorites. And so here's a picture from us one in the plains, and you can see the tips of the mountains here sticking out of the ice shield. And you can see how the ice is sort of like flowing, right? They look like big glaciers. And so right here, that would be a good spot where the ice kind of like stalls against the mountain and where the wind can ablate the ice. And that would be a good spot to go and look for meteorites. So this is what our field camp looked like. And so when we were in Antarctica on the plateau, right, here are our little tents. There, 2 people can fit in there to sleep. And we were the only living organisms in that place for hundreds and hundreds of miles. So it took a couple of days for us to get here. And then this is what it looks like on the ice field. And so here's a meteorite that we found on the ice, and you can see how black it is. Again, that's the fusion crust. And you can also see that it doesn't have any sharp corners. And that's because when it enters the atmosphere and it starts melting, all the sharp corners that the meteorite might have had, they get rounded off because it melts a little bit. And so you can still see edges, but they're all rounded off. And so here again is me all bundled up. It's very, very cold in Antarctica. And here's a picture of one of the meteorites. We take pictures and it gets a number, and then we pick it up with sterilized tongues. And so here you can see the picture. This meteorite broke open when it hit the ice, because the ice is really hard, and so the meteorite broke. And so here you can see how thin the black fusion crust really is, and you can also see that the inside of the rock looks very, very different than the outside. And that's an indicator as well that this is a meteorite. So because there are mountains sticking out of the ice, and then these are the areas that we search, but we also search these fields where there are lots of earth rocks, right? And now it becomes a game of like, can you spot the one rock that is different? So when I was in the field, I took a couple of pictures, and I'm going to show you this. So here's a picture. There are lots of earth rocks, but there's one meteorite in this picture. So I'm going to give you a couple seconds. Look at the picture. Remember that meteorites usually tend to be kind of rounded. They kind of tend to be black on the inside, and they're different color. They're black on the outside and slightly different color on the inside. So if you look at this picture, can you spot the meteorite? And so there is the round black one on the left. Let me see if I can put up the chat again. Yeah. Do you mean, I assume you mean maybe this one, the big round one? Yep. Yep. That's right. So this is the beginner level. Hold on. There. This is the meteorite. So good job, everybody who guessed this meteorite. Now we're gonna make it. We're gonna step it up a little bit. Another picture. Now, if you look at this very carefully, you know, meteorites come in all sorts of shapes and sizes. And so here are lots of different little black rocks, right? And so this gets a little bit more tricky of like which one is the meteorite. And so I just like take a look, I'm going to give you a couple seconds, and then I'm going to show you which one it is, and then you can tell me whether Ria's mom says it's one at the bottom left. So maybe this one here, the charcoal medium-sized one on the left. Okay, yeah. All right, I'm going to reveal this one is the actual meteorite. All the other little black ones that you see here, there are little ones here, there's one here, up here. All of those are earth rocks. So you can see it gets a little bit tricky. So now, if you got that one, good job. Now we're going to go to the expert level. So here in this picture is another meteorite hidden. And you can see that sometimes in Antarctica, it gets quite tricky depending on what the lightning conditions are. And so we at first did not see the meteorite either. It took us, we discovered it honestly by accident. And so I can tell you it's not the big one. And a lot of people think it's this one. It's also not this one, even though it does look very different than all the other rocks. So the meteorite in this picture is this one. You can see it sits right underneath these two, and you can see the black crust on the outside, and you can see here where the crust is broken, you can see that the inside looks different. So that's the meteorite. And so that took us a couple minutes. That took us like 10 minutes until we realized we actually were sitting here on this big rock having a lunch break. And then we hopped off and we were like, oh, there's a meteorite right underneath. And so then we collected that one. So that was a fun day. Okay, so what comes next? Let's say we have a meteorite. And then how do we know where it comes from? And what are the next steps in science? What do we do with it? And so I have a nice video for you. What we do is we do X-ray computed tomography, or XCT, and that is something that is often used in medicine. So if you go to the doctor and you say you have a lot of headaches, they might put you in a machine and they CT scan you, and then they get a 3D image of your brain without actually cutting you open. And so we can do the same thing with rocks. For some reason, Google Slides won't let me play it, so I'm quickly going to stop sharing, and then I'm going to share the video with you differently. Okay, let's see if that works. We're going to share this. Okay, hold on. All right, oops. Let me scroll this all the way back. Okay, so here we go. So this is the moon. So this is a meteorite from the moon, and we scanned it, so we get the 3D movie, and now we can slice through the meteorite and we can see the interior. There are lots and lots of little different rock fragments in there. And then we also discovered that there was a melt vein in it. And so what we can do with these data, we can make everything invisible except the things that we are interested in. And so we were interested in the melt. And here you can see a 3D rendering of where the melt is in the rock. And that helps us to see what's on the inside of the rock. And then if we want to cut the rock open, we can now make an informed choice of where to cut the rock so that we can expose the things that we're interested in. And so the movie is just starting. I'm just going to let it run one more time so you can really see what it is. There's the melt vein going through right here. Lots of different little particles and minerals in this rock. And now we're zooming back out, and we're making everything invisible except all the little melt pockets. They are now glass, but they used to be melt, and it went through the meteorite or through the rock in these cracks. And so now we can really see nicely where these melt formations are within the rock. And so now we can cut it right here, or maybe right here, so that we can expose it. All right, so let's go back to the presentation. Share this one. Okay, I hope you can see this. All right, so once we know what the meteorite looks like on the inside, we're going to cut it, and we're going to cut it exactly so that we can expose the things that we are most interested in. And so here's a chondrite, and you can see there's a big clast right here. And so we cut it right in the middle so we could expose this. And then we slice it, and so we turn that into a slice. And then we glue that onto a glass slide, and we grind it down thinner than a human hair. And we do this, we call this a thin section. We do this because then we can shine light through it. And so that means we can put it under a microscope, and you can see how the light shines through here. And so we can look at the texture of these of these meteorites. And so here's a picture of what it looks like if you were going to look through the microscope. And so you can see they are like big minerals right here. They're all these little white minerals, right? And so you can get a good sense of what the textures look like. But we have special filters on these microscopes that we can put in, and then the color of the mineral changes. And based on the color, we can identify what type of mineral it is. And so this is what it looks like when you put the filter in. And now you can see there are also all these little bright ones that are in between the white ones here, these needles. And the ones that look like one big grain turns out to be multiple little grains. And so we can identify these minerals, and we can then say, oh, you know, this is an apatite and it can only form when there's water around. Or, you know, these are olivine and pyroxene, and they only form when there's a lot of pressure in it. So it has to come from a place on the inside of a planetary body. And so once we have these thin section, we've taken all these pictures, we can then look at the isotopes of the rock. So every solid material in the solar system has isotopes and oxygen isotopes. And there are 3 oxygen isotopes, oxygen 16, 17, and 18. And oxygen 16 is the most abundant. And so we can ratio 16 to 17 and 16 to 18 and look at the different ratios. Now, everything on Earth falls on this line. See the dotted line here? That's the terrestrial fractionation line. So different processes on Earth have turned the oxygen isotopes into different categories. So Earth atmosphere plots right here, and then all the rocks on Earth plot right here, and then the oceans of Earth plot right here. Now the moon also plots where Earth plots, because the Earth and the moon, they have a common history. They formed together. But all the other rocks in the solar system plot very differently. So Mars is the little red dot right here. Here we have ordinary chondrites, and then these are carbonaceous chondrites. So they come from different planetary bodies, different asteroids. And each asteroid basically has its own little blob right here. So depending on where in the solar system you have formed, how close to the sun or how far out from the sun, you will have your own little oxygen isotope ratio. And so once we measure the oxygen isotope, and let's say it plots right in this field, then I know that the chondrite that I'm looking at belongs to the CK group or something like that. Another thing we do is we look at the minerals themselves. And so every mineral, when they form on a planetary body, they have a different ratio of iron and manganese, right? These are 2 elements. And so we can plot iron and manganese on a diagram, and then each planet has a different trend line. So all of Earth rocks, you can see in blue, plot here. All the moon rocks plot slightly different, and all the Mars rocks plot up here. And we know this because we actually went to the moon and picked up rocks. And so we can directly compare those to the meteorites. And we have rovers on Mars that measure the chemistry of iron and manganese. And so we can compare that measurement directly to meteorites. We also have some material that plots right here from asteroids. And even though we don't have rovers there, we can look with telescopes, and that gives us an indication of what the iron and manganese ratio is. And so we sort of know if they are coming from Vesta, for example. But if we have a meteorite that doesn't plot on any of these trend lines, then we honestly don't know where it comes from. If it has a different oxygen isotope ratio that we haven't seen before, and it has a different iron manganese ratio that we haven't seen before, then we can only speculate, right? We don't know for sure where that meteorite comes from. All right, and before I'm going to stop talking, I'm going to show you my personal favorite meteorite. This is Allen Hill's 81005. That meteorite comes from the moon, which happens to be my favorite planetary body, although I also really like Mars, but I do like the moon a little bit better. And this meteorite was found in Antarctica in a region called Allen Hills. And so the first 4 letters come from that region where it was found. And it was found in 1981. And so that's the first two numbers here. And Allen Hill's 81005 was the very, very first meteorite as being recognized coming from the moon. And you can see that it's composed of all these different little types of rocks. And this is a type of rock that we call a breccia. And a breccia is a treasure trove because it contains all these little rock clasts that come from all sorts of different regions on the moon, all put together into one rock. And so as a treasure trove, it doesn't contain gold, but it contains knowledge. So this is a treasure trove of knowledge from a big, big region on the moon. And if me as a scientist, what I'm trying to do is I try to unravel every little secret that all of these different rock types contain, and then I'm trying to understand how the moon and the Earth formed together. And so with that, the only two main things I would like you to remember is that meteorites are windows into the interior of planetary bodies. So if we want to learn something about the inside of Earth or the inside of other planets, we need to look at meteorites. And meteorites are very, very important because they help us understand how planets formed, how the solar system formed, how old the solar system is, how old our Earth is. And so they're very, very crucial for science. And that's why I like them so much. And that's why I like my job so much. And now I'm happy to answer any questions. And thank you so much for listening to me. I'm going to stop sharing now so I can potentially see you or at least see the chat. All right. I forgot what I was going to do. Lauren?
Google Docs.
Thank you. All right. Okay. Oh boy, questions over questions. Okay, so let's start at the top. We have a question of what are you looking for inside the meteorite? Why is it important to know where to cut? Oh, so when you have a rock, you obviously cannot look on the inside, and sometimes a lot of the meteorites are breccias, like the one I showed you. And so they contain different rock fragments or melt veins that I just showed you. And so we use these melt veins to date the impact from where the rock came from. And so if we just randomly cut the meteorites, we might not be able to expose that melt vein onto the surface. And so if we scan them first, then we know what cool stuff is on the inside, and then we can orient it and cut it in a way so that we can expose the things that we would like to see. All right, let's see. How many meteorites did you find in Antarctica? Oh, that's a good question. So when I was there, as a team, we found 263 meteorites total. And so we found a really, really big one that was about the size of a basketball. So that was super exciting. And that's pretty average for a field season. Sometimes if they found lots of meteorites, like smaller ones, then the numbers can go up to like 900. But we found more larger ones, but fewer of those. And so our total haul was 263. Philip would like to know, do you need to decontaminate a meteorite? Oh, Philip, that's a really good question. And so when we go to Antarctica, we try not to touch the meteorite because we don't want our bacteria and gunk and all sorts of stuff to like be on the meteorite, right? So we are very careful not to contaminate the meteorites with us. We have learned from bringing back samples from the moon that the space rocks don't contain anything that can harm us. And so we don't really have to decontaminate a meteorite, also because when it enters the Earth atmosphere, a lot of stuff burns on the outside. But we need to make sure that we protect the meteorites from us. So that's the bigger problem. That when you have a meteorite sitting on Earth, it interacts with the Earth atmosphere, and we have bacteria everywhere, and so then they go into the meteorite. And then, you know, if you don't know this and you look at the meteorite, and let's say the meteorite comes from Mars, and then you look at it and you're like, oh my God, there's a bug in the meteorite. There's life on Mars. But in reality, it was a little bug that just crawled into the meteorite while it was sitting on Earth. And so it is more important to protect the meteorites from Earth or from us than to protect us from the rocks, basically. All right, Ria's mom would like to know, if organic matter and microbes were on asteroids and came to Earth, is it possible that some of the life originated from outer space? And would that mean that the planetary bodies of where the asteroid came from would also have the same microbes that came to Earth? Ria's mom, that is a very good question. So to date, we have not found microbes on asteroids or in meteorites. We have found amino acids. And so primarily glycine and some other biomolecules and compounds like nucleobases and sugar compounds. And these are key components of DNA and RNA. So these compounds made it to Earth on meteorites, right? If the meteorite hit Earth, then Earth got contaminated with those. And so it is possible that life components were brought to Earth from meteorites, and then on Earth, they then evolved into life. But because these are only compounds, there's no evidence that there are microbes or life on asteroids. Also, asteroids don't have atmospheres. So if you don't have an atmosphere, there's a lot of radiation. And so the surface of these planetary bodies that don't have atmospheres, that surface gets sterilized. And so no life can really exist right on that surface. And so for Mars, for example, there we have the Perseverance rover right now, who's actually looking for signs of life, because we also have found compounds of key ingredients that we need for life on Mars, like phosphor and nitrites, which are compounds of DNA. But we have not found any evidence that there actually is life on any other planetary body but Earth. All right, Karen would like to know, in the future, can Earth get a ring? That is a very good question, Karen. It's a really fun question. So the answer, unfortunately, is no. However, so we have a moon, and Earth has gravity, so it's kind of pulling things towards us. Now there's a radius that's called the Roche radius, and so if everything stays outside that radius, the moon is just happily gonna go around us. If it was going to come closer, then Earth gravity and the tug and pull of the sun would basically rip the moon apart, and it would turn into a ring, just like Saturn. However, our moon is moving away from us very, very slowly, kind of like at the speed of how your fingernails grow. So no, we will not get a ring from our moon. If we were going to capture, let's say, an asteroid or something, and that comes too close, and then that gets ripped apart, we could potentially get a ring. However, when that happens, big pieces will also start raining down on our surface, and that will probably kill a lot of people. And so I personally hope this is not going to happen. Could we ever get another moon? So the moon and the Earth formed at the same time through a giant impact that formed the Earth and the moon at the same time. There are planets out there like Mars who have moons, and there are captured asteroids. And so, yeah, we could maybe get another moon by capturing another big asteroid. But that would have big implications, because it will probably change the tilt of Earth, and then will change all the seasons, and then we'll probably all die because Earth is going to freeze over, or it's getting really hot or something. Our climate will not be stable anymore. And the rotation of our Earth might also change. And so it is possible. I don't think any time in the future, and I'd rather not, let's say it that way. Okay, let's see. Philip would like to also know what tools to use to cut a meteorite. Oh, that's a good question. We use saw blades that are dusted with diamond powder, because rocks are usually really, really hard. And diamonds is the hardest material on Earth. And so if you have a saw blade, they're usually round, and they spin, and then you go ahead and like you cut the meteorite over it. If it's covered in diamond dust, then we can very nicely cut the meteorite. Sometimes we use something called a band saw, where the saw blade is basically just a tiny string. And we use that if the meteorite is very small and we don't want to have a big cut. So a band saw is used when we have very precious material, like Apollo samples from the moon that the astronauts brought back, or sometimes we do this with Martian meteorites as well. All right, and then Shravanti would like to know, how can you identify a meteorite in a field among other rocks if you're not a scientist? That is a really good question. So when I went to Antarctica, right, and I'm a scientist and I actually work with meteorites, I was really scared that, you know, I would go there with all these other people and that I would not be able to actually identify a meteorite. I had total anxiety about this. But the cool thing is, once you're on the ice, and you go, the meteorites actually look different, and it's kind of hard to explain, but the surface, it's rounded, it's black, and it has this little bit of like a glaze to it. And Earth rocks don't have that, and so our eyes are very, very good. All the eyes of every human, even your eyes and any person who's listening right now, our eyes have the ability to spot things that are different from other things. So if you are in a field of rocks, your eyes are so good that they can spot the one rock that looks slightly different. And so if you just like survey, you know, a field of different rocks and you're like, wait a minute, that rock looks different. Then you go and you pick it up very carefully, and then you can see if it's a meteorite or not. Sometimes if we really can't tell, and if it's a very primitive meteorite, if it's from an asteroid, there are little metal particles in there, and so then we could hold a little magnet to it, and if it's magnetic, then it's most likely a meteorite. But some earth rocks are magnetic too, so sometimes that's not so good. All right. Jack would like to know, are there any meteorites on Pluto? Oh, you mean on Pluto? That's a really good question. You know, I would think that they are. You know, if we have pieces of rock that get thrown out into space, and if they travel beyond our gas giants, they can potentially land on Pluto. Absolutely. The problem is that some of the gas giants like Saturn and Jupiter, they have a very big gravitational pull just because they're very massive. And so if meteoroids from the asteroid belt get thrown out in that direction, they will more likely land or fall into Saturn and Jupiter and then burn up in the atmosphere. But you know, it is totally possible that there are pieces of meteorites on Pluto. Absolutely. Yeah. We know that there are meteorites on Mars because we have found them with the rovers, for example. We know there are meteorites on the moon as well because we found them. And so there are other planetary bodies where we know there are meteorites on there. And so it's definitely, yeah, it's possible that there are meteorites on Pluto. We just, you know, ideally would go there and find it, but Pluto is kind of far away. All right. Are there any projects considering recovering meteors from the ocean? Oh, that's a really good question. There are projects where we sort of monitor the atmosphere, and if something enters it, we can sort of track it. And there has been one instance where a meteorite fell fairly close to the coast, and we tried to recover it. The problem is once it lands in the ocean, it disintegrates fairly quickly, and also it gets contaminated with the ocean water because that water seeps through the entire rock, and so we've tried that and it hasn't really worked out very well. You know, I sometimes say for fun, it would be great if we could put big nets under the ocean surface and then collect all the meteorites that fall into the nets. But, you know, then fishing wouldn't be possible. And I'm pretty sure all the ocean life would also not be happy if they couldn't surface because we have gigantic nets under the surface. So yeah, unfortunately, all these meteorites are lost to science, but there's nothing we can do about it. All right, Ria's mom would like to know, has water ever been found in meteorites? That is a very good question. The answer is yes, but maybe not in the form that you are thinking of water. So water, as in liquid water in our oceans, no, that would not be in meteorites because if it enters the atmosphere, it just, you know, evaporates. However, there are certain minerals that can only grow when water is around. And one of these minerals is called apatite. And so what happens when an apatite crystallizes, it builds the water into the crystal structure. And we have found those minerals in meteorites on the moon, from the moon. We have found these from meteorites from Mars. We have found them in meteorites from asteroids. And so that means that on that planetary body from which that meteorite is coming from, that there had to be water somewhere. And so, and sometimes that water is in a magma, it's like on the inside of the body. dissolved in a magma chamber, for example. And so, yes, we can measure the water in these minerals, and we can also measure the composition of the water, or the isotopic composition of the water. And it's different from the water that we find on Earth. All right, let's see. Are meteorites always named after where they are found and the year? That's a very good question. The meteorites are usually named after where they are found, yes. So let's say you find a meteorite, you have to submit you have to get some chemical analysis done to actually show that this is a meteorite. And then there is the Meteoritical Society that classifies the meteorites, or you classify it, and then they say you can have an official name. And so that's the nomenclature committee. And so you can submit your classification. You can say, hey, I found a meteorite, and let's say I found it in New Brunswick, and so I want to call this New Brunswick 2021. And so you submit that to the nomenclature committee, and they meet every week, and they go through all the submissions, and they make sure the data looks good, and then they can say yes or no, and then your meteorite has an official classification. And so usually meteorites are named after the city, or if it's close to a city where they were found, that's how they get their names. Yes. All right, Philip would like to know, what is the largest meteorite ever found? Oh, that's a good question, Philip. The answer is the Hoba meteorite in Namibia, which is in Africa. It measures about 9 by 9 by 3 feet, and it weighs 60 tons. The fun part about this meteorite is it kind of looks a little bit like a pancake, if you think of it. And there's no crater. There's no crater associated with this meteorite. So what we think happened is that this meteorite came at an angle into Earth's atmosphere, and it skipped like a stone through the Earth's atmosphere. So it slowed down so much that when it actually landed on the surface, it didn't make a crater. So when you skip a stone through over water, this is what we think happened with that particular meteorite. So that's a cool fun fact. And then we have Matt and Jason, who would like to know, have you found any asteroids that were in the Oort cloud? Oh, that's a good question. I don't think so. Also, it will be really hard for us to really know that they were from that region. What we have found are pre-solar grains. And so those are grains that come from outside of our solar system. And so they could potentially come from the Oort cloud or other places outside of our solar system. And so they existed before our solar system actually existed. Yeah, so these were all wonderful questions. Oh, there's one more here in the chat. What does the 005 after your favorite meteorite mean? Oh, that is, you just continue to count. So that's probably the 5th meteorite that they found in that year. Okay. If that is all questions, I'm just going to refer back to Lauren and Patty.
All right. Thank you so much. Go ahead, Patty. You can take us out.
All right. Thank you so much for a wonderful presentation. Every time we talk about this, I learn a little bit more of your research, and I put in the chat an actual picture of a rock that you cut that we were invited from the museum. So if for the question that what was the tools, you can see it in there. And it's an experience, right? Like I never imagined what I was going to see. So look, whenever you're curious about something, just find someone that could show how it's done. That's the magic of science, right? We try to do things that nobody else have done. So we learn every day. And with your research, it's like everything is new every single time. So thank you so much for your presentation. We miss you here. We love your style and your research. So we hope our audience enjoy as much as we did this presentation tonight. And if you haven't done so, please fill out our survey link that was in the chat. We want to know if you like these academic year's activities that we have for you virtually. We are crossing our fingers that we will be back in person in the fall, but if not, we definitely have a tool and a model that we want to stay in contact with you. And please, if you have ideas of what you want to see, let us know. And we have one more Ask a Geologist coming up. Is with Dr. Rosana Grafals from the University of Puerto Rico in Calle. And she's a geographer, so you're going to see a different perspective on the geology and maybe some anthropology. So we hope to see you not this Friday, but the following Friday at 1 p.m., Friday at 1. So stay tuned for more information with us on social media, and have a great night. Thank you for tuning tonight. Bye.
So that's May 14th for everyone. The
May
Ask a
14th.
Geologist,
Thank you,
May
Maria.
14th.